So the next topic is finite automata in compiler design in unit 1. So we are going to see what is finite automata in compiler design. Okay. So first, what is finite automata? It is a state machine that takes a string of symbols as inputs and it changes its states accordingly. So a mechanism that recognizes a set of valid inputs before carrying out an action, and also a notation for describing a family of languages recognizing algorithms. It reads the operation of the machine is nothing but finite control. It reads the current letter of input under the tape head. So this is called tape head here. So transit to a new state depending on the current input and the current state as it is dictated by the transition function. So it is halted after consuming the entire input. Okay. So transition which can show the initial state, inputs and next state as written as delta of q comma a on q, it is on a when it is entered on q, and a it is moving to the transition on the b state. So for example, how you are going to write the transition function here, delta of q0 on 0, it is reaching q1 state. So here also one example is given, delta of q0 on 1, it is reaching q2 state. Okay, we can see the more examples. So basically it represented as a graph or a mathematical functions or in a tabular form. So we have three types of forms in finite automata, that is graph and tabular data and the mathematical functions. So this is the mathematical model of finite automata. So where q is nothing but finite state of state, and which is sigma is nothing but finite alphabet, and delta is nothing but transition function, that is a total function from q to sigma is, it is also called q. So q0 is nothing but initial state, f is nothing but final state, so it is also called qf. So for first thing we are going to represent this finite automata in finite state diagram. Okay. So finite automata, it is a recognizer for regular expressions. When a regular expression string is fed into finite automata, then it changes its state for each return. If the input string is successfully processed and the automata reaches its final state, it is accepted. So that is the string just fed was said to be a valid token of the language in the head. So here we can see the graphical representation of finite automata. So on it is QA, it is a starting state. On A transition, it is going to reach another state that is called QB. So here it is represented as starting state and double circle represented as final state. So what is automata? We are having two types of automata here. First one is DFA, that is deterministic automata, and non-deterministic automata, that is also called NFA. So what is deterministic automata? It is nothing but each move is uniquely determined by the current configuration. That is a single path. In DFA, we have only one path from one state to another state. But in NFA, we have multiple moves possible in from one state to another state. Cannot determine next move accurately because we have multiple moves. So we are unable to determine the next move, which we cannot find the exact accurate state. It may have multiple next moves or multiple paths. So an automation whose output response is limited to yes or no is an acceptor. So which is also accepts the input string and either accepts or rejects it. It measures the complexity, that is nothing but running time and amount of memory which is being used by the transition diagram. So finite automation is also used as a limited and constant amount of memory, which is very easy to model and which we have limited applications. So here W is accepted by A, then the configuration is Q, from Q0 to W is the configuration F to epsilon, where F is an accepting state. So the language is accepted by A, which is written L of A is defined by W implies W epsilon sigma star, which is W is accepted by A here. So whereas DFA is nothing but every move is completely determined by the input and its current state. Okay, we have only one state here, one input symbol, finite control device. It can be any one of the states. That is nothing but Q. Q implies Q. May contain trap or dead states. So our DFA may contain dead states also. It may contain accepting states. So we can see the examples here. So what is DFA? It has start state and QT. It is trap for the strings and that can start with A and B, accepting state that cannot be reached. So QF state, it is the final state of the transition diagram. Q1 is state reached after any B in a string that started with an A sigma equal to A comma B. So these are all on transitions, how it is mentioned. So delta of Q0 comma A on Q0, which is entering on A, it is reaching final state. On Q0 on B, which is reaching QT state. Again on QT, from QT state, it is reaching on A, it is moving to the same state, QT. So for QF on A, it is moving on the final state. QF is nothing but here final state. So on Q1 on A, it is reaching QF state. So these are all the input symbols here. These are all the QF is the other states. So for this example, we are going to construct here transition diagram. See here, all these we have mentioned in a transition function, right? Delta of Q0 comma A is QF. On Q0, when it is on A, it should reach QF, right? So on Q0, on A, it should reach QF. Here QF means we have final state here that is represented by the double circle. Q0 on B, it should reach QT. Okay, Q0 on B, it should reach QT. Again here, QT on A, it reaches same state. QT on A, it reaches same state, A. So QT on B also, it is reaching same state. QT on B, it is reaching the same state. Again, QF on B, it is reaching Q1. On QF on A, it is reaching the same state. So Q1 on A, it is reaching final state. Q1 on A, it is reaching final state. QF on B, it is reaching Q1. Okay. So for this transition function, we have designed the transition diagram. Okay. Suppose if we have all the items cost 40 coins, then coins accepted are 5 coins and 10 coin and 25 rupees coin. Okay, consider this example. So recall again, these all the mathematical model of finite automata. So what are the entities here? Q is a set of states. What are the states here? Possible states. We are going to represent sigma is the alphabet and delta is the transition here, and we have to take Q0 as a starting state and QF is the final state. F for Q0. Okay. So what are the possible states in this? What are the possible state in this example? See here the status of the machine before and after any of the alphabet symbols have been applied. So what are the input symbols? the coins which are giving as a coins here. How do we move from one state to another state? Transition when a coin is deposited. When we are exchanging our coin, then the transition is applied. Where does the machine start from? The beginning. So initially we can start from the beginning. F is the final state. When it reaches the 40 coins, then that is the final state. So if you have more than 40, then what is the situation? Design state first by partitioning sigma star, then starting from BB, then starting from again contains, see here, for this, from starting from Q naught, it reaches on, so here we are writing transition diagram and transition functions, transition table. These all called it as a types of finite automata. So on Q naught, we can take this is as a starting state. Okay. So on Q naught on A, it is reaching the Q naught on A, it is reaching the Q naught. Q naught on B, it is reaching Q1 here. Again, Q1 on A, it is reaching Q1 on A, it is reaching Q naught here. Q1 on B, it is going to final state. That is nothing but Q2. Again here, Q2 on Q2, it is reaching the final state. Okay, Q2 on A, it is Q2, Q2 on B, it is also Q2. So here the final state is Q2 here, and this is sigma. What are the inputs here? Only we have A and B input symbols here. And what are the states here? Q means set of states. That is Q0 and Q1 and Q2 here. This is all nothing but a finite automata. So all these are designed using our finite transition diagram. Okay. So we are going to see in the next class what is non-deterministic finite automata. Okay. So this is also comes under in the finite automata. Okay. Thank you for listening.